Hi students, in the second video for online lecture 2, let's now get into chapter 2 and talk about atoms and elements. But one of the first things that we need to do is talk about the scientific method. This is important because we need a systematic approach to doing all of the research and all of the observations that we are going to talk about. It's really important to observe something, but if there isn't a plan involved, then we are going to miss something. So one of the things that we want to do is start with our observation. But even before the observation, we are needing to do a hypothesis. Remember that a hypothesis is talking about why we are doing a study. But then we figure out what our observation is, and then we try to represent that. That might be a mechanism when it comes to organic chemistry, that might be a cell structure when it comes to some biochemistry, or just a balanced chemical equation. But the biggest part is that we then need to interpret that. This is where one of the issues comes involved because sometimes the interpretation is wrong. As you've seen in many forms of data, many forms of science, and just things in general, interpreting the data incorrectly doesn't get us to a correct solution. We also need to have the ability to go and rethink our observation. We have to be able to go back, recalibrate, see what's different, and to see if our representation and a further interpretation is correct. So the biggest thing about this is understanding the different types of data. There's qualitative data, general observations. Well, what does that mean? Well, that might be color changes. That might be observations of, oh, this bubbles. Oh, this does this. It doesn't have any data associated with it. The best way of explaining good qualitative data is it's hot. If I put my hand on something warm, I can say that it's hot. But that's qualitative. It doesn't have a numerical value with it. So then we can look at the quantitative side. This means that we're going to comprise our observation with numbers obtained by measurement. Instead of just saying something is hot, I can say, oh, this solution is at 95.2 degrees Celsius. Notice that there is a little bit more scientific background. Qualitative is good. We don't ever want to short how good our observations are, whether something's bubbling, whether there's a color change. But really good data comes from the quantitative side, and we have to be able to have a balance of both of them, so that way you can get a full view and understanding of your reactions. The reason that quantitative data is so important for us is that we use a standard set of equations and units. We want all of our data to be universally understood and accepted by anyone who is willing to do that work. If we use different equations, there's going to be a lost in translation, and we don't want that. So throughout this course, when we use equations, we are going to use the commonly accepted equations for many of the studies that we are going to do. So let's talk about the scientific method part by part. The initial observation is probably the most important. This is what makes scientists scientists, and that is that inquisitive thought of, hey, what's going on here? Think about it. If you have your television remote not working, you're saying, my initial observation is it doesn't work. So the nice thing about it is that's the first side that you need to have, and that is just having that thought of, hey, something's not right here. Then we can go to our hypothesis. This is a tentative explanation for a set of data. The nice part about a hypothesis is that you're commonly going to go and test, then modify, then test and modify. Your hypothesis is never, ever, ever going to be 100% correct at the beginning. And that's a good thing because we want it to be based on scientific understanding and fact, but we don't know everything. And that's what brings joy to science, is having an understanding of the problem, but always being surprised by the results that we get. So once we do the hypothesis and get the idea, that's when we run our first experiments. Then we take a step back. We look at the data. We try to do our observation in what do you see? So the initial observation is, what is my original problem? The data collection is, What did I gain from my experiments? The nice part about it is that you can always go and do a new round of experiments. In the lab, we typically ask you to do certain experiments 2 to 3 times just to see if it's repeatable with precision and accuracy. But the nice part about it is you go into further studies, you're going to create a new round of experiments with the ideas based off of your first one. One big issue that we see, not only in the sciences, but in common course of human society now, is how we treat data. The data tells the story. Do not fit the data to the story. This is where, if you have a hypothesis, so many people are willing to go in there and take the data and say, oh, this confirms what I already knew. But that may not be the case. Look at the data and say, oh, this is a change in what I expected. I can tell you personally, in my own times of studying biochemistry, every time I went in sure that something was going to happen, it never happened that way. So let the data do exactly what it's supposed to and what it is going to do, and then you worry about how to then frame that and explain the story. So how do you explain it? Well, there's two ways. Typically, we have what is called a law. You have heard of probably many laws in physical science, the law of conservation of mass. Well, then there becomes an issue. What is a law? It's a summary of observed behavior. This is a summary of what actually happened. These are results. So when we talk about the law of conservation of mass, it is based off of this is what will happen. But let's talk about theory. We talk about the theory of relativity. Well, that's probably one of the most famous physics ideas out there, and we'll talk a little bit about that in our course. But a theory does a tentative explanation for the behavior or the observation. So the interesting part in here is that a law explains exactly what happens. Theory is the explanation or a tentative explanation. Theories are always changeable. So this is what we are going to want to do, not only when we start to look at some of the ideas over the next few videos about the creation of the atom and its structure, but then as we're starting to go through many of the fundamental ideas later on in the course, you have to look at it and say, is this a law or is this just a theory that helps explains the observations? So let's look at our first example for this video. Which of the following parts of the scientific method is illustrated below? A scientist records in his lab notebook that the reaction turned from clear and colorless to a dark yellow color while giving off gas bubbles if he increased the amount of reactants. So the question becomes, what do I have here? Well, I have A, which is analyzing my experimental results. B is creation of a law. C is forming a hypothesis. D is the initial observation. And E is the reevaluation of the hypothesis. We know that we are not going to create any laws because even though we have observations, we are not going to explain any of that. So now, what do I actually have? We are really between two questions here, and that is analyzing the experimental results and our initial observation. How do I know the difference between answer A and answer D? Well, it's actually harder than you think. Remember, initial observations happen and say, why are we doing this? It is before any experiments have accomplished. Based off of the paragraph, this scientist has done the experiments and he is recording the observations. So the correct answer for this example is going to be A. We are analyzing the experimental results. We are looking at what happened and being able to explain it. So the correct answer for this problem would be answer A. So what does it mean to be a good scientist? This can be very difficult in many cases. And over my 15-year career and the beginning of your career, this is going to be something that you should all strive for. It will not happen overnight and should be as systematic as possible. There are two major goals. We want to have good prediction and we want to have control. But control can be very dangerous. So if you go back to the movie Jurassic Park, they were saying we can predict and create dinosaurs and we can control them with fences. Well, you saw how that control worked because the dinosaurs ended up getting out and eating everybody, and then they made 4 later movies where dinosaurs just kept eating people. That's a really dangerous idea, and there's a very neat monologue in there about control in science. So let's go with better goals. The best goals to have when dealing with science is understanding and explanation. One of the most horrible events during your lifetime is Hurricane Katrina. Do we have any prediction? Yes, they predicted for days, this is where this is going to hit. But did we have any control? Absolutely not. So once they had the prediction, then comes the understanding, trying to get people to evacuate, explanation on why the levees failed the way it did. So as you go through this, you want to be able to get away from the idea of control and start with understanding and explanation. So what makes a good scientist? I have 4 things listed here. The first one is knowledge. That is why you're in school. You are wanting to increase your knowledge on certain topics. You are not expected to know everything. You never will. But having the ability to increase your knowledge and become more thoughtful about the explanation of things can be really, really helpful. Number 2 is something that most people struggle with, including myself, and that's just patience. You have to be able to methodically work through the scientific method in order to see if reactions are going to work the way that they're supposed to. Too many times scientists want to rush through results or take snapshots. Instead of going and running a reaction 2 or 3 times, they may only do it once and say, this is how it has to be. Patience, patience, patience. I know you're going to want to get into a hurry to get through your sophomore, junior, senior classes, get on to your professional schools, your med schools. But being slow and methodical and working through there is going to help you greatly, because we want you to make sure that you are systematically working through the fundamental steps that you need. The third thing is having sound technique. This is what you will gain by being in the lab, possibly doing undergrad research. Having sound techniques is what makes a very good scientist. Knowledge is great, but as you've also heard, having that balance of can you physically do it is really impressive. I may have all the knowledge in the world of trying to be a famous ballet dancer, but if I don't have the techniques, you'll never see me with the Moscow Ballet. The fourth one can be very, very fickle, and that's luck. So many scientists in this world will always say, oh, I knew this was going to happen, or this is just, I expected this. But luck plays a very big role in what we do. That might mean doing reactions on day in which the humidity is down, understanding that molecules are going to do what they want to do. Maybe it's coming in at the right time for a project and new technology being created. Luck plays a very important role in what we do. As long as you understand that, you can benefit from it as you're going along. I have 4 basic rules for all of the students that I have when it comes to science. 1, your results should be reproducible. Nothing is more frustrating in this world than having a scientist say, oh, this is how this is done. Okay, let me try it, and not being able to reproduce it. One of the things that is so frustrating with internet videos and how-to videos on YouTube is that you might want to go and fix something, but then you can't reproduce it. Well, then how good is that video really? So results that you do should be reproducible by others. Second one is you should have detailed research reports that should be viewable. Science should be transparent. It should be understandable. So I know many of you are going to get very frustrated when it comes to writing down your results and turning in your DRAs and being graded. But we want to hold them to a high standard, because if you're going to do scientific research in your time at A&M, you should get the basis set on what you need to have, and you should be able to have someone look at it and go, hey, I get that. That makes sense. The data and the science is good. 3, conclusions should be reasonable and unbiased. One of the things that we get with scientists is we do get a lot of bias depending on what discipline you're in, the way it's explained, and we don't want to have that. What happens if someone at that other school in Austin were to go and cure cancer? Are we going to remain biased even though that benefits human society? Absolutely not. We need to give people their due credit, and we have to look at the science at the level of can we understand it and is it good for the overall community. Finally, the last one, which is as important as anything, is giving credit where credit is due. Citations, citations, citations. You have to be able to cite where you get ideas from. As you've probably seen in the time in the video, when I ever make kooky jokes, I will tell you what movie they're from. A lot of the knowledge and pop culture I get come from the movies that I watch, but it's not original thought. So I have to be able to cite and tell you where that comes from. That is true about scientific explanations and citation of others' work. So let's talk a little bit about the beginning fundamentals of the idea of the atom. We can go all the way back to Greek philosophy. They were the first person to talk about the indivisible atom. That's where it comes, atmos, meaning indivisible. But Dalton was really the first person to really start to understand about atomic structure. He stated that number one, elements are composed of extremely small particles called atoms. He took this idea from the Greek roots. He took atmos and turned it into atoms. So now we are saying that elements, our fundamental building blocks, are made up of actually building blocks that are all identical, and we are going to call those atoms. All atoms of a given element are identical, having the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. Now you're probably reading this, and this statement is partially true. Not all atoms of a given element are identical. We are going to talk about that here in a little bit when we deal with isotopes. This means that they may have a little bit different size and mass, and it could change the chemical properties. But the biggest thing here is the atoms of one element are different from the atoms of all other elements. This is true by the number of protons, and we will talk about that in the next video. Compounds are composed of atoms of more than one element. In any compound, the ratio of these numbers of atoms of any two of these elements present is either an integer or a simple fraction. This is when we start bringing up the idea of the whole number ratio. We are not going to have fractions of atoms. If we need to have a ratio of 2 to 1, this means that we must have 2 of one and 1 of another, not 1 and 1/2. We are always going to talk about them as full parts of a system. And finally, a chemical reaction involves only the separation, combination, and rearrangement of atoms. It does not result in their creation or destruction. This was predominantly true up until about the early 1940s, in which we started doing atomic chemistry. So all of the reactions that we are going to do are going to be talking about separation, combination, rearrangement of atoms. Once you get to Chem 120, then we can start talking about nuclear chemistry and what it takes to break an atom, how we can have different types of radiation. But for the most part, this is still holds true with a little exception here and there. In the next video, we are now going to talk about how the atom was actually built, how we determined the fundamental particles of the proton, neutron, and electron, and how the representations give us some clarity into Dalton's atomic theory. Have a great day.